the organic compounds may be carbonaceous biochemical oxygen demand or nitrogenous biochemical oxygen demand. So it is CBOD or NBOD. BOD means, once again, biochemical oxygen demand. Biochemical oxygen demand means we are talking of in aerobic environment, the decomposition of the organic matter. This chapter needs to be clearly understood because it is a very important chapter, and also some amount of numericals are also involved in this. Now, what is called 5-day BOD test? 5-day BOD test is basically you measure the dissolved oxygen, DO dissolved oxygen initially, and dissolved oxygen at the end of the decomposition, divided by dilution fraction P. So 5-day BOD test is a measure of the oxygen demand in that particular organic wastes. Now, so today we will talk about examples of, we will take some examples. So far, we have assumed that the dilution water added to the waste sample has no BOD on its own. Now, while we do the biochemical oxygen demand, actually we take the sample water and then we mix it with, we dilute it with some amount of water. Now we can assume that this added water does not have any BOD on its own. Now, to sort out the effect of seeded solution, for example, there's another important equation, which is BOD M VM is equal to BOD W VW plus BOD D and VD. What is this equation? Let us know. Where biological oxygen demand M is equal to BOD of the mixture of wastewater and the seeded dilution water. Seeded dilution water is certain amount of dilution water which is required for the experiment to take place. BOD W is equal to BOD, biochemical oxygen demand of only wastewater. BOD D is equal to biochemical oxygen demand of the seeded dilution water alone. Seeded dilution water alone. VW is equal to the volume of wastewater mixture. Wastewater mixture. VD is equal to the volume of VD is the volume of the seeded dilution volume of the seeded dilution water in the mixture, and VM total volume of the mixture. The mixture. P is equal to fraction of, yesterday we had come across the term P, fraction of the mixture is equal to actually VW divided by VM. So 1 minus P is equal to the fraction of the mixture is the fraction of the mixture is equal to actually will be VD by VM. VD by VM. 1 minus P. So BODW from this equation from 1 we may write BODW is equal to BODM VM by VW minus BODD VD by VW into, let us say, VM by VM. Vt by Vw, Vm by Vm from here, from equation number 1. Okay. Now, so therefore, we can write BODW is equal to BODM divided by, let us say, VW by VM. We can write VW by VM minus BODD VD by VM. We can also write VD by VM into VM by VW. VM by VW. So this can be written as BODM divided by VW by VM minus BODD. We can write VD by VM divided by VW by VM. So this further simplifies into now P is equal to, we have already found out P is equal to 1 minus P is equal to VD by VM. So from there we can write BODW, therefore BODW is equal to BODM minus BOD D into 1 minus P divided by this is P. BODM is nothing but dissolved oxygen initial minus dissolved oxygen final, and BODD is equal to BI initial and BF final. BI actually is the new term. Initial dissolved oxygen DO in the seeded solution. Seeded solution is the solution which is added for dilution, and BF is equal to final DO, final dissolved oxygen, in seeded dilution water. So finally, we can write that BODW. So finally, we can write from here. This is, if we say this is equation number 2, from 2 we can write BODW is equal to DO initial minus DO final minus BI initial minus BF final into 1 minus P divided by P. So BODW, the final expression for the BOD of the waste itself, BODW is we are trying to find out if there is a certain quantum of waste, organic waste, that is dumped into a water reservoir, then what is the biochemical oxygen demand of that waste? And later on we have to find out that if this oxygen demand is being taken out by that biochemical by the waste, in that case we have to make a risk assessment as to how risky is the aquatic plants and animals in that environment. This for which these mathematical expressions are required in order to predict its biochemical oxygen demand. Okay, now there is just before, in the last class we had also seen that there are carbonaceous biochemical oxygen demand and nitrogenous biochemical oxygen demand. Now, what are the equations for those? Let us find out. We'll talk about the nitrification first. All these, the previous discussions were taken into account that these are all carbonaceous organic waste. If it is a nitrogenous organic waste, then what are the treatment we have to find out first of all. So the nitrification, because nitrogen is a very critical element which is required for the protein synthesis, and hence it is extremely essential to life. For example, nitrogens the soil which is rich in nitrogen is good for the plants to grow. That's why you will find that the nitrogenous fertilizers are used mostly for the growth of the plants. Now, in the aerobic environment, it will be 2NH3 plus 3O2. It gives rise to 2NO2 minus plus 2H plus 2H2O, and 2NO2 minus plus oxygen, which gives rise to 2NO3 minus. This is Nitrobacter, and this is called Nitrosomonas. In presence of this, it takes place. Therefore, conversion of ammonia into nitrates requires then oxygen. So hence nitrification of organic wastes also has its oxygen demand. So we already know that nitrogenous oxygen demand that we have touched upon. Now, with this, what we shall do, problem on nitrogenous oxygen demand. Domestic water or we can call it wastewater. Domestic wastewater has 30 milligram per liter of nitrogen in the form of ammonia. Assuming that very few new cells of bacteria are formed during nitrification of the waste during the nitrification of the waste find one, the ultimate nitrogenous oxygen demand. Number two, the ratio of the ultimate NBOD to the concentration of nitrogen in the waste. This is the problem. Solution. We know 2NH3, the earlier equation 2NH3 plus 3O2 gives rise to 2NO2 minus plus twice H plus twice H2O, and we also have 2NO2 minus plus oxygen further gives rise to 2NO3 minus. Okay, so these are the two things we know. Therefore, combining these two equations, we can write this goes off. So 2NH3 plus 2O2 gives rise to NO3 minus plus H plus H2O. How it comes? Let's say, if we combine these two, this is 1 and this is 2. If we combine, finally, it will become 2NH3 plus 4O2. Let me write. Sorry, 2NO2, ये दोनों ऐड करने से क्या होता है? This will cancel out 2NH3 plus 4O2 on the left hand side. On the right hand side, you have got, 2NO3 minus plus 2NO3 minus 2NO3 minus plus 2H plus 2H2O. 2H2O. Okay. So, so basically, so in that case, finally it becomes NH3 plus 2O2, 2 निकल गया, NO3 minus plus H plus H2O. This is the formation we have got out here. This comes by adding 1 and 2. 1 plus 2 add करने से we get this one. So now NH3 means NH3 molecular weight (14 plus 3 into 1 is equal to 17). O2 molecular weight is equal to 32. So therefore, this particular equation means 1 mole of ammonia 1 gram mole NH3 requires 2 gram mole of oxygen. Now 17 gram of ammonia contains 14 gram of nitrogen. Concentration in the problem, it is given that 30 milligram per liter of nitrogen in the form of ammonia. That concentration is given. So therefore, concentration of nitrogen is 30 mg per liter. Therefore, NBOD, nitrogenous biochemical oxygen demand, is equal to your 30, this is mg per liter, into 17 gram of ammonia divided by 14 gram of nitrogen into 64 gram of oxygen divided by 17 gram of ammonia. If we calculate, it will be 137 milligram of oxygen per liter. Second part is called the ratio of the ultimate NBOD to the concentration of nitrogen in the waste. NBOD we have already found out. Now the concentration of the nitrogen in the waste is already given. Of nitrogen concentration of nitrogen in the waste is given as 30 mg per liter. Therefore, the ratio of NBOD to waste concentration is equal to 137. Excuse me, just a moment. So ratio of NBOD is 137 divided by 30 is equal to 4.57 milligram of oxygen per milligram of nitrogen. This is the answer. So So fairly simple chemical stoichiometric calculations. Although you are out of touch for a long time, so am I also. So, but a little bit of concentration, this will see us through about this. This is a very important chapter as far as the decomposition of the biological organic wastes are concerned. Okay, so this is all about this one. Now, today, one more thing we would like to discuss. What is the syllabus? I'm displaying the syllabus. Now, water pollution, water sources, unusual property of water, the hydrological cycle that we have completed. Now, surface water quality, rivers and stream, biochemical oxygen demand, water quality in lakes and reservoirs. This we shall do it in the next class. Water quality in lakes and reservoirs. And then we will discuss about the noise pollution. Today we will not discuss any more any more new chapters. So we will discuss about the noise and noise pollution and the water quality in lakes and reservoirs, that we shall discuss. There is a thermal uh, pollution of the water bodies that we have already taken up, and we also did one numericals on this thermal power plant. If it is rejecting certain amount of wastewater, not this the wastewater, it is basically in the thermal power plant, what it does is that it takes in the water because the working fluid is water. It takes in the water from the river, it goes through the processing plant, it purification is done. Purification is mainly done due to prevention of sedimentation in the pipelines, because in thermal power plants, basically the heat interaction has to take place between the working medium, which is your water, and your fuel is coal. So therefore, the temperature, the heat transfer has to take place between the coal and between the flame and the water. In between, you will have the pipelines. So therefore, we have to take an utmost care that the pipelines does not get sedimented. So therefore, the water is basically passed through the treatment plant, and then it is fed into the boiler. Boiler also have lots of pipings, because if you see this, if you see the cycle of Rankine cycle by which the thermal power plant works, is that the same water goes into the boiler, becomes high pressure, high temperature steam. Then the high pressure, high temperature steam through a jet, it falls onto the blades of the steam turbine, thereby producing continuous power, continuous mechanical power. And the mechanical power on this thing, uh, uh, on on the steam turbine shaft, you couple the generator, and the generation of electricity is happening there. Now this particular, the exhaust steam which is coming out from the turbine is being fed into the condenser. condenser, the function of the condenser is to cool the exhaust steam into hot water. This hot water is filled into the well, and the condenser, through the cooling tower, the warm water is being thrown into the pond or the large water bodies under which by the side of the which the power plant is situated. So as a result of that, a certain amount of warm water, hot water, is being ejected into the river, so which actually leads to the thermal pollution. Therefore, the it also endangers the species which lives in the rivers. Okay, so that is the that is it. That is the thermal pollution, and we shall. I think today we end the class here itself, and we shall meet on Friday, and we will discuss about the module 3, the last chapters, which is the noise pollution and the arsenic contamination and the noise pollution. Probably I will take 2 more classes to complete the module number 3. After that, we will go for the module number 4. Module number 4, which is the environmental management system or environmental engineering and management system, ISO 14000, that we shall talk about in the module number 4. Thank you very much for attending the class.